Welcome back, PlayBASIC coders. Let's dig a little deeper than what we normally do. Here's a program that on the surface just seems like it does nothing. It's running through, and each one of these images is a different image format, a different depth. And we're rendering this side as solid and this side here is transparent. In other words, the mask color is being eliminated from these blits over here. So if you think about that for a second, that means that if you have the source surface and the destination surface in the same bit format, the colors are in the same format, a 15-bit image has pixel data that is like this. There's an unused bit, there's 5 reds, 5 greens, 5 blues. That's 555. (16-bit) is very similar. It's 565. We have 1 extra green. That's it. 24-bit is 3 bytes, where each red, green, and blue channel is full 8-bit, but we're using 3 bytes. So we have I've got that right. 8 R's, 8 greens, 8 blues. So that takes 3 bytes of memory. These two formats here take 2 bytes of memory. And 32-bit is pretty much, the same as 24-bit. But we have another channel for alpha, which is not really used in PlayBASIC unless you're using the AFX services. Then you are using a full 32-bit surface. In that case there, it's 4 bytes of where each channel is 8 bits in scale, right? So if you wanted to draw a 32-bit surface here and map it back to a 15-bit surface, you have to pluck out the appropriate bits, 5 bits of R, 5 bits of green, 5 bits of blue, stick them all together, and then you get the final color that you can write to memory. One of the things that PB was missing, it's not really true, there's a bunch of fillers in it generally for doing copies between different surface depths. So you could copy a 15-bit surface to a 16-bit, 24, 32-bit, and all of those back. Now, obviously, if there's 4 different surfaces, there's potentially 16 different combinations. Now, some of those are repeated, If the source and target are the same format, it's just a pass-through. So in this case here, there's one routine that does, if it knows the source and destination are the same bit format, and it's 2 bytes per pixel, we can use these same routines to do both formats, but we can't use it for this one here. 24-bit is very frustrating to work with, because internally, the CPU it prefers to read integers on aligned boundaries, and these aren't. If you've got a frame buffer with pixels, you've got 3 bytes for this first pixel, the next 3 bytes is pixel 2, the 3 bytes after that is pixel 3. They're not evenly on nice 4-byte boundaries. If they were, we can grab it from memory quite comfortably and throw it back into memory quite comfortably as well. When it's not, we've got to pick it apart. If if we want to modify the pixel, it's annoying, etc. So what this demo here is showing, it's almost invisible to the naked eye that we are, we are converting these formats in both forms, a solid blit and a transparent mask color blit. And that's what you see. The left 4 images are a solid blit. So this is, the background is 15-bit. You can tell in the banding you see through here. And as the background image is changing depths, we're getting more color data per pixel, so the gradients look smoother and smoother. What we're missing, what we had problems with, there were some combinations of these fillers. 24-bit had a few broken ones, but it wasn't just those though. There was a few 16-bit ones that I'd optimized at some point and probably messed around with and not actually either gone back to the original or superseded an old version or superseded a new version. One was completely wrong actually. A couple formats would just crash. Now, in the real world, in most of the time for PlayBASIC users, you would never run into this. Underneath the command sets, when image data is moved around and loaded in particular, this is the copy features that are used to move the data between different formats. So if you load an image that's 16-bit into memory, yes, and the current surface depth is 32, it gets upscaled to here. That's why you need to have these blits. And that's why they were generally solid, opaque blits that didn't worry about mask color, because they were just used to copy buffers, directly as you went through. Now, all the sprite engine has had this ability for a long time, but the image copying was missing some combinations, as we just talked about. There's some other places too that are missing the same combinations, and we'll go to the recent Wolf demo here. It's a bit convoluted to follow, but hopefully you'll understand what I'm talking about. What I've done, well, I'll go back to the other format. I'll just mask the text, all the textures. So we've got the X loop. So here I'm using the X loop as to be the R component of the color we're going to draw, and the Y loop is the blue component. There's no green in this at all. So we're just ignoring the texture and making these what should be a nice clean gradient in between red and blue. If we have probably scale it up a bit actually. Scale up here by 2. Because the texture sizes are like 64 by 64, so they're quite dark. Yeah, okay. You're probably going, what the hell are you talking about? Well, notice how the screen depth here is 32-bit. So that's an ARGB surface. It's very easy to read and write from a modern processor. Lovely. So all of our vector graphic stuff all works pretty well with this stuff already, because it's been written for that for eons. The texture strip commands didn't. So these textures that we're using for the walls, even though I've got rid of the actual images for a second and we've put gradients in their place, you can see the gradient's not nice and smooth. The steps are quite large, because in 15-bit we only have 32 possible levels of shade for the red, green and the blue. If we change the texture resolution, 24-bit, now you can see it's a better approximation for a smooth gradient. 32-bits should look the same. Okay, so what that means is that we can have our textures in 15-bit and render them to a 32-bit screen for vertical strip rendering. They can be 16-bit, 24-bit, and any mismatch here is now handled by a generic filler. It's not very optimal, but it doesn't really matter. It's just there for worst case scenario. Now the screen depth, I can do the same thing. If we have 32-bit textures and I turn the screen to 15-bit, it looks the same as before because the screen now only has 5 bits of R and blue and green, but the source texture has 8 bits of R, 8 bits of green, so the bottom 3 bits are being lost. Right, they're just being effectively truncated away. Okay, so this is another thing that we couldn't do before. Like old PB couldn't do this. And there was a handful of these built-in commands that don't have this facility. So you could stumble upon a combination maybe if you would not, and be kind of bemused what was going on. I remember running into this myself a few times where I wanted to keep textures or keep images in a different depth than the actual screen resolution to save a bit of space, and you generally don't need full 32-bit. Like 16-bit is actually a pretty good approximation. The characters here, the guards, they're internally 32-bit being mapped down to whatever the screen resolution is, because that sprite rendering stuff I wrote years ago handles all of this for us, handles all the blend mode combinations, all of that stuff for us. That's why it's big and such a convoluted piece of code. But for these kind of effects, they're just combination heavy. If you have a source texture and a destination texture that are 4 different possibilities, that's 16 combinations of fill routines. If you have, 2 different methods, a solid render method and a transparent or mask color method, that's 32 combinations. So I could blow out very quickly. So what I've done here is I've made a generalized version of those routines when the source depth and target are different. That's it. That's all I really wanted to say. This version here is more obvious. This keeps a part of the texture. So we'll scale up the X and Y so the red and the blue appear a bit more, and we'll run him again. Now the green channel of the texture walls, right, is exactly that. It's just the green channel, and the other channels are our gradient. So we're losing some information from the texture when we do this, but that's okay. But we're running 15-bit wall textures and rendering them out onto the 32-bit frame buffer. That's for vertical strips. I haven't actually patched the horizontal strips, but this will actually give you an indication of what I'm talking about, that you need these things to be corrected. I think it's in the test here somewhere, is it? Yeah. So this is just drawing the normal vertical strip. And if we add up just a horizontal strip in the same loop, if our source texture and our destination buffer are different depths, we will not get something that looks reasonable. For vertical strips, we'd often just crash the application. Hopefully that won't happen. And straight away we get a nice mess. Okay, so our wall loop is rendering the walls vertically and horizontally there as well. What's our target? So our screen depth is 32-bit, and it is using the 16-bit image data, but because it's, see how the texture is repeating and scrolled like that, what's actually happening is that it's treating the source texture as if it was 32-bit, so that the data is just all in the wrong spot for it. 24-bit source texture, hit the 32, now we're fine. Because the source and destination are the same format, so it's reading and writing that same pattern. If we made the destination 15, 16-bit, and the texture's 15-bit, it all works fine. We need those combinations to just flesh out that part. And this is the kind of tedious stuff that you end up having to do. And I've had to remove and deprecate actually some render paths because they're entirely written in assembly and there's no need for them anymore. I'm going to use the same rendering code. This is why I'm so dogmatic about getting this stuff to work perfectly or be very bug tolerant. It's going to work reliably, and so when I put these things back together, we don't get bizarre results. We don't get, is it the compiler that's breaking things? Is it the runtime that's breaking things? Is it the command set that's not behaving the way it should be? Nothing worse than when everything's all fresh code and you get lots of undesired results. I think that pretty much does it, really. If I have the gradient in the background, it's much easier to see the difference between a 15-bit frame buffer and a 32-bit frame buffer. You can see the color banding, not just in the video. So our destination buffer, our screen is 32-bit, and we've got, you know, blue up here, green, red, whatever it's up here, I don't know what it is. If we go to a 15-bit frame buffer, we'll see all the banding. Right, means all that stuff there is rendering the same stuff, but there's a version to draw this in 15-bit format to that kind of buffer. I mean, the irony of this in particular is that these old textures and sprites, they're actually 8-bit. That means it's 1 byte per pixel, and each byte has a potential color. Each byte is used as a color index into a palette of 256 colors. But there you go. I mean, you can see the difference using different color depths. I would definitely advise not against using 24-bit for most things. It's kind of, the engine supports it, but it's not an optimal path. Generally, the most optimal paths are 16-bit or 32. And that will probably be the case going forward. Most 24-bit stuff will probably cease to exist, or there will cease to be custom code for rendering that stuff. It'll just be like generalized, you know, simplified routines. Some of those routines work quite well, to be honest, particularly on modern processors. Anyway, thanks for listening, and we'll see you next time. Bye.